We're the Mars Rover team at Johns Hopkins University. In our second year as a team, members from our 5 sub-teams have been diligently making progress to prepare for URC's 2025 competition.
This season, the mechanical sub-team completed designs for all systems and is in the process of completing the final base and arm prototypes in preparation for competition in late May. For the base, we developed an aluminum rocker bogie chassis with a robust differential bar to increase stability on various terrains. The system is supported by our custom-designed 3D printed wheels. The tire hub system uses TPU for flexibility and PETG for durability with a safety factor of 2 for worst-case loads. For object environment manipulation tasks, our 5 degree of freedom mechanical arm moves on a linear stage with elbow and wrist articulation. A fully rotatable gripper enables tool handling, object lifting, and keyboard interaction. Currently, we have a miniature prototype and are finalizing the manufacturing of our final ARM product by the end of March. The Science subsystem features an excavator-inspired scoop that holds about 9 grams of soil and sand. The rotating rod design allows us to dig soil samples and transport them into our 3D printed funnel. The soil is transferred into cuvettes in a custom-designed carousel which organizes the samples and acts as a centrifuge.
The biochemical subteam has developed protocols for chemical tests that can detect peroxidase, glucose, and sulfates, respectively with TMB and H2O2, Benedict solution, and HCl and BaCl2. Using the scooping mechanism, 1 gram of soil will be deposited into each chemical test in the carousel's cuvettes. In 12 test tubes on the carousel, we plan to test 9 soil samples with 3 different chemical tests. The last 3 test tubes will be used for untested soil collection. After centrifuging the samples in the carousel, each one will be analyzed with an ocean optic spectrometer. Based on a thorough literature review, the team has chosen specific wavelengths for each assay that reflect the presence of relevant biomolecules. The rover will collect the absorbance data and transmit it back to the team members at home base, who will conduct quantitative analysis using principles like Beer's law. The team has created and fitted standard curves for each assay such that the absorbance data collected on-site can be converted to concentration. Additionally, the team has benchmarked soil samples from our very own Hopkins campus, Utah, and Nevada to create a thorough baseline for analysis on the day of competition.
The software subteam has worked on interfacing sensor readings with the motors, implementing basic teleoperation for the base, and developing autonomous capabilities.
We developed custom libraries to collect and filter IMU data and GNSS readings to calculate optimal paths to target coordinates, as well as help with obstacle avoidance. We also created a ROS2-based publisher-subscriber framework for communication with our motors to control speed and direction. For base teleoperation, our team implemented arcade control on a smaller version of the rover's base. We also developed a leader-follower system to control the arm. We have tested this using the miniature arm as both a leader and a follower, using this mode to transport objects and type on a keyboard.
For autonomous navigation, our rover detects 3 key objects: an orange mallet, a water bottle, and an AR tag. To detect the mallet and water bottle, we trained a yellow V11 model on a dataset we built using RoboFlow. To detect the AR tag, we used OpenCV's Aruco library. Since the Mars Desert Research Station has a red-hued landscape, we also trained the model on black and white images to improve detection in low-contrast conditions. For the mallet, water bottle, and AR tag, we estimate distance using the area of the detected object's bounding box, moving the rover forward until the object appears large enough in the camera frame.
The electrical subteam works closely with the software subteam to advance programming progress and develop communication systems. We developed an ad hoc network for our 2.4 GHz antennas to transfer data from the GPS IMU spectrometer and multiple camera streams. For onboard communication, we are using the CAN serial protocol alongside custom software and firmware. We specifically designed the onboard computers to promote ease of configuration. The complexities of changing tasks will instead be handled with the clicking of a button in software. We have an effective power distribution board that simplifies the kill switch on our rover, as well as provides wiring support for the regulators, computers, motors, and sensors.
Thanks for watching. Hope to see you in May.